A quantum particle does not behave like a tiny marble hiding at one exact point. But it also is not just a fog of probabilities. The Wigner function is a way to draw quantum behavior on a map that looks almost classical. Put position on one axis, momentum on the other, and write W of x and p. If W were an ordinary probability cloud, every region would be 0 or positive. But quantum waves can interfere, and interference leaves something stranger, negative shadows. The definition looks like a Fourier transform of coherence. W of x, p equals 1 over pi h bar, times the integral of psi star at x plus y, psi at x minus y, e to the 2ipy over h bar, dy. In plain language, it compares the wave function on both sides of x, and asks what momentum pattern those pairs imply. For a calm Gaussian wave packet, the Wigner function is a bright positive blob. It behaves almost like a classical particle with uncertain position and momentum. But make a quantum cat state, a superposition of two separated packets, and the space between them grows stripes. Some stripes are below 0. Negative Wigner values do not mean negative chances. They mean, no ordinary joint probability over position and momentum can explain this state. The negativity is a fingerprint of genuinely quantum interference. That is why Wigner functions are useful in quantum optics and quantum computing. They let us visualize when a system is merely noisy, and when it contains a resource that classical randomness cannot imitate. So the key idea is simple: the Wigner function is a phase space shadow of a quantum state. Positive blobs look classical. Negative ripples reveal the hidden wave nature underneath.